A capacitor is a device that holds charges on its surface to store electric energy as an electric field. Capacitance C of a capacitor is calculated by dividing the amount of charge Q on the positive plate by the magnitude of the potential difference V between the plates. Therefore, C is equals to Q over V. Geometry. Two cylinders with radii R1 and R2 make up a cylindrical capacitor of length L. Let R2 be greater than R1. The exterior cylinder is grounded. We may disregard the electric field fringing at the endpoints because the cylinder is long enough. The magnitude of the radial electric field at a point between the cylinders depends on the separation from the central axis. Calculation. Number 1. Calculating electric field. Consider a Gaussian surface with length y and radius r, where r lies between r1 and r2. Because the electric field and area vectors are perpendicular to each other, flux through the plane surface is 0, that is, the angle between E vector and ds vector is theta equals 90 degree, such that cosine of theta will be cosine of 90 degree, which is 0. And that gives us the flux is equals to the closed integral of E vector dotted with the area vector, which is equals to the closed integral of E ds cosine of 90 degree, cosine of 90 being 0, we get a 0 flux. For the curved path, the angle theta between the electric field and the area vector is 0 because both are in the same direction, and the flux will be equals to phi is equals to the closed integral of E dot ds, which is equals to the closed integral of E ds cosine of 0 degree, and that gives us closed integral of E ds. Due to the symmetry of the geometry of the chosen Gaussian surface, electric field is constant such that phi is equals to the closed integral of E ds, that will become E times the integral of ds, and that gives us E times A. Equation number 1, with A being the total curved surface area of the cylinder, which is given by A is equals to 2 pi times R times Y. Substituting this value of the area A in equation 1 to get flux phi is equals to E times 2 pi Ry. So this is equation number 2. Let Q enclosed be the total charge on the inner cylinder's surface such that Q enclosed is given by Q times Y over L. Using Gauss's law, the flux through the surface will be phi is equals to Q enclosed over epsilon naught, which is equals to Qy over L epsilon naught. This is equation number 3. Equating equation number 2 and 3, we get E times 2 pi Ry is equals to Qy over L epsilon naught. Solving for electric field, we get Q over 2 pi epsilon naught times R times L. This is equation number 4. Number 2. Calculating potential. Recall that VA minus VB is equals to negative times the integral E dot dr going from RB to RA gives the potential difference between 2 points A and B. In our case, VA and VB represent the inner and outer cylinder potentials respectively. RA will be R1 and RB will be R2. Thus, VA minus VB is equals to V, which is equals to negative times the integral E dot dr going from R2 to R1, which is equals to negative times integral R2 to R1 E dr, because electric field and dr vector are both pointing in the same direction. Using the value of electric field obtained in equation 4, we get V is equals to negative times integral Q over 2 pi epsilon naught times R times L times dr, with the limit value going from R2 to R1. And that gives us negative Q over 2 pi epsilon naught L. So this being constant, we have pulled it out of the integral. times integral R2 to R1 dr over R. Now we change the limit. Since there's a negative sign, we use a property of integral, so we have positive q over 2 pi epsilon naught times L. Now the limit goes from R1 to R2 and we integrate 1 over R. So the integration is natural log of R, which when we put the limits, we finally get q over 2 pi epsilon naught L times the natural log of R2 over R1. So this is equation number 5. So following from the definition of capacitance obtained for parallel plate, C is equals to Q over V. So we replace the value of V here. So we have Q divided by Q over 2 pi epsilon naught times L multiplied by natural log of R2 over R1. So C will be equals to 2 pi epsilon naught L whole divided by the natural log of R2 over R1. Note: charge is only stored on the inner cylinder of a cylindrical capacitor. The outer cylinder is earth, so it will be free of charge. When a plate or conductor is earth, the potential at that point on the surface is 0. Result: therefore, the capacitance of a cylindrical capacitor of length L is given by C is equals to 2 pi epsilon naught L whole divided by the natural log of R2 over R1.